tonight your homework will just be page 13 to 14. And then tomorrow I'll go over some of those problems as well as do page 15 and 16 for in class. And then in the class, I'll just walk around and check that you guys have done page 15 and 16 that we did in the class. And then I'll be able to have all the grades for your from your worksheet 1 and worksheet 2, sorry, packet 1 and packet 2. And those homework grades are all going to go towards your first assessment test that you guys took earlier this week. So, and I hope to have those grades in the grade book probably end of.
So we're type 13 to 16 or 13 to 14?
13 to 14, and then we'll do page 15, 16. Yeah. So I sent out a reminder yesterday. I'll send out a reminder again today. Yeah. So let's go to page 10. As we work through all of page 9. I know you guys did the homework already, but I want to walk through these things here. So we've been seeing these theorems more recently because of the free response questions that we've been practicing with, like extreme value theorem and mean value theorem. So extreme value theorem. The whole purpose of extreme value theorem is being able to find the highest and lowest points on the graph without the use of a graph in front of us. So we're kind of relying on certain piece of information, basically looking for candidates where the highest and lowest points of the graph can exist. So if a function is continuous on a closed interval, then the function must have a max and a minimum y value on the interval. And the candidates that we're going to look at are endpoints and critical points. So critical points we find by setting the derivative equal to 0, because wherever the slope is 0, those are going to be the potential places where your peaks and valleys are, right? Your hills and valleys. So we want to look at where slope is 0, and also if there's a denominator, then we want to set the denominator of the derivative equal to 0, because if I have a place where the slope is undefined, that slope undefined could actually end up being the place where the maximum can occur. And then after we find our candidates from our endpoints as well as our critical points, we're going to insert all of them back into the original function and then compare the y values. Highest y value is your absolute max, lowest will be your absolute min. Okay, so here's number 1 on page 10. Find the value of the absolute extrema on the function on the interval from -2 to 3. State the theorem and conditions. So I want to find absolute max. This is a EVT. So we can say that our function is continuous, first of all, on the closed interval, because it's a polynomial. So there's nothing that's going to prevent, there's no asymptotes, there's no holes. Okay, it's just a smooth curve here. Okay, we already know what the endpoints are, so we know we're going to test -2 and 3, but we want to find, are there any other critical points that we should be concerned with? So the way we find critical points is we set the derivative equal to 0, right? Where the slope is 0, or where the slope is undefined, either way, it's going to come from the derivative, so we're going to set the derivative equal to 0. So we go through power rule here. Right, set the derivative equal to 0, factor out a 6. Now, are both of these valid candidates for our EVT process? where do these critical points have to live? Yeah, between the interval, right? So if it's outside the interval, then it's not part of our problem, right? So 2 is between -2 and 3. That's good. So is -1. So we have 4 points to test. And they all go back where? How do we test them? Yeah, original function, right? We want to find the highest and lowest y values. Right? So when we do that, we'll just one by one put it into the function. So -2 gives us a y value of -3. Plug in -1, I get 8. Plug in 2, I get -19. Plug in 3, I get -8. So between these 4 values, the lowest I see is -19. The highest I see is 8. So absolute max is 8. Absolute minimum is -19. The x value is not that important. You can leave these out and be perfectly fine. It's the y values that's that the problem is asking for.
It'll be marked off though if you state the x value.
Right, but if you say that the absolute max is x equals -1, then that's not what the AP exam is looking for. They're looking for the y values. So if it's multiple choice and they're asking for absolute max, and the choice is between 8 and -1, 8 is the correct answer. -1 is the location, but it's not the max value. Okay, so we've also seen mean value theorem more recently because of the FRQ test that you guys took. So again, mean value theorem is trying to just guarantee a slope. You know, if I'm given a function, can I guarantee that somewhere along that curve, there's a specific slope that's going to exist on that curve? So we first have to establish our conditions. Is our function continuous on the closed interval? Is it differentiable on the open interval? And then we're going to find our endpoints and find the slope between the endpoints, set that equal to the derivative function. And when we do that, we're able to find the location on the curve where the slope that we're looking for exists. If it's a slope of 2/3, then we can find that slope, that location of that slope 2/3. If it's a slope of 10, then we can find a place where that slope of 10 exists. Okay, so let's go through our steps here. This is more of a calculator question here. Number 2, let the function be defined by x plus natural log of x. What is the value of c for which the instantaneous rate of change is the same as the average rate of change? This is also an indication of mean value theorem because instantaneous rate of change, that's f prime. Average rate of change, that's f of b minus f of a over b minus a. So without stating mean value theorem, they're describing it in a way where we're basically applying mean value theorem. Okay. So let me highlight what this is. The average rate of change is this portion of the formula there. And the instantaneous rate of change is the derivative. So we're setting the instantaneous rate of change equal to the average rate of change. That's another way of saying mean value theorem. Okay, so we have our endpoints. We can find the slope between the endpoints. We can find the derivative function. We're going to set them equal to each other. So first, though, I'm going to find the endpoints, or find the endpoints and find the slope between the endpoints. So let's find our endpoints here, f of 1 and f of 4. And this is a calculator question, so we can enter 1 and 4 into the function using our calculator. So f of 1 is 1 plus natural log of 1, which is 1. F of 4 is 4 plus natural log of 4, which is around 5.3. And then we want to figure out this portion of our formula. So f of b minus f of a over b minus a. So our average rate of change ends up being 1.462. So that's one piece that we need. The second piece that we need is from the derivative. So we're going to set f prime equal to this number. So f prime, think about our derivative. We can go through rules that we know. X becomes what? And then natural log of x becomes 1 over x. Okay, so we're going to set them equal to each other. Okay, this is not an easy problem to solve algebraically, but that's why we have a calculator here. What we can do is we can bring everything over to one side. 1 plus 1 over x minus 1.462 and set equal to 0. And now the strategy here is if we use our calculator, we can graph this function and then look for the what? X-intercept, yeah. Wherever the graph crosses the x-axis, that's going to be the solution or the location that we're looking for, the decimal x value that we're looking for. All right, just to show you what that looks like here, if I have 1 plus 1 over x minus, okay, I'm going to do zoom 6 here. See where across the x-axis, looks like it's around here. And if you look at your answer choices, it's all around between 0 and 3. So I'm going to just adjust my window because I know that all my answer choices must be between 0 and 3. So I'm just going to go from 0 to 3. And that way I can just kind of focus in on the parts that I need to look at. And it's still hard to see here. So I'm going to make my window not show as high or as low. So let me just go from like -2 to 2. I'm just picking some random numbers here. Okay, so there's my x-intercept, right? So I'm going to do second trace 0. Pick a point to the left of the x-intercept, scroll to the other side of the x-intercept, hit enter again. And it should find that x-intercept for us at 2.164. Okay. Rolle's theorem is virtually identical to mean valley theorem, but it's just a more specific version of mean valley theorem. It's a more restrictive version of mean valley theorem. We still go through the same process. We're still finding slope between the endpoints. We're finding the slope. But then between the two endpoints, if it's Rolle's theorem, what do the two y values have to be? The same, yeah. So the idea is that mean valley theorem, the slope can be anything. It could be slope of 1/2, could be slope of 3/5, could be slope of -12. But with Rolle's theorem, we're trying to guarantee a slope of 0. So if I want to get a slope of 0, I need the 2 points to be directly across from each other to share the same y value so that we can draw a horizontal line to create that slope 0. So that's the distinction between mean valley theorem and Rolle's theorem. It needs the endpoints to produce the same y value. Otherwise, we can't guarantee that there's going to be a slope 0 between. Let f be provided by f of x here. Let find all the numbers C that satisfies the conclusion of Rolle's theorem such that f prime of C is equal to 0. Okay, so we go through our conditions here. Our function is continuous and differentiable because it's a smooth curve. State those conditions out. Okay, and also we need to find the endpoints. So we'll plug f of 0 and f of 3 into the function and see if they give us actually the same y value. So if I plug 0 in, what do we get? If I plug 3 in, 27 minus 27 plus 1, I still get 1. So these points are actually directly across from each other. So if I graph it, you don't have to graph it, but I want to show you. This is 0, 1 here. This is 3, 1 here. We know that if the graph goes through, all right, if it goes through those points, and if I can draw a horizontal line between it, we know that somewhere between there must be a place on the curve where there's also a slope 0. Right, so we've established that our function will guarantee a slope 0 somewhere between 0 and 3. So now we're just going to set f prime equal to 0. Okay, we don't want to set equal to 1, right? Because we're not trying to guarantee a slope of 1, we're trying to guarantee a slope of 0. because 1 minus 1 over 3 minus 0 is equal to 0. That's my slope. So I'm going to set f prime equal to my slope. What's my derivative? So now I'm going to look for where on this curve is there a slope of 0. So simply setting my f prime equal to 0 and then solving for x. But where does my x value have to live? Between the interval, right? So technically there's another place of slope 0 at -√3, but we only care about what's between our intervals. So our only c value is √3. Okay.
I see positive retreat.
I'm sorry?
Why see this positive retreat?
Because c is the x value. We're trying to guarantee a slope 0 between these two endpoints. So there are two places where there's a slope 0, but if there's a location that's outside the interval, then it's not part of our problem. So -√3 is outside the interval. Now, if both of your answers are outside the interval, there's something wrong because we're guaranteed that there's at least one solution. So there must be at least one c value that lives between the endpoints. Okay. Page 11, there's a miscellaneous list of problems. I do want to go over, we went over a cone problem yesterday. I do want to go over a cylinder problem because the cylinder problem, the formula looks like a cone, but it's a lot easier. But because we do more cone problems, the tendency is we want to treat a cylinder problem like a cone problem, but there's a distinct difference that makes cylinders easier. So we have a cylindrical tank with a radius of 5, being filled with water at a rate of 3 cubic centimeters per minute. So I just want to draw a cone just for comparison purposes. You don't have to, just want to show you. So imagine water is filling in both of these tanks. Okay, I want to talk about the radius and the height of the water level. Here, as the water is coming in, is the height changing of the water inside the cone? Yes. Okay. Is the radius changing? Yes. Yeah. So as water is coming in, the radius is going to change. The water is leaking. The radius is going to change as well. Okay. Now moving on to the cylinder here. Imagine water is coming in. Is the height changing? Yes. Is the radius changing? No. No. So that's the big distinction. Okay. The radius is not changing. The radius is a constant, which makes the problem easier because with the cones, we actually had to keep track of both the radius and the height. That's why we have to go through similar triangles, because we couldn't just replace one with just a number because they both keep changing. But with the cylinder, a radius, as soon as we know what the radius value is, we can replace it. There's no need to do similar triangles with cylinders. However, the reason why we may get tricked into doing that is because sometimes problems provide information that is needed, that is not needed. They would say, the height is, 4 feet. And then they would say that, maybe the container has a height of 10 feet or 10 centimeters, right? And then they give you all this data to see if you will start setting up a similar triangle and kind of lead you down the wrong path. So just be aware that with cylinders, sometimes you may get additional information that is not needed. So with cones, we need all that information, but for cylinders, we don't, because we're not doing similar triangles. There's no triangle involved here. So here's our formula. V is equal to pi r squared h. It says the tank has a radius of 5 centimeters, which means that the water is also experiencing a radius of 5 centimeters. And we know it's not going to change, so we can just go ahead and get rid of it. Just go ahead and replace it. So what would that look like? V is equal to what? I make that substitution. 5 squared times h. And as soon as we make that substitution, we're ready to find the derivative. It's a lot faster. There's no need to go through a different set of similar triangles and solving for r, solving for h. We can just jump directly into our derivative process. Okay, that's what makes it easier here. Okay, let's find the derivative. V becomes what? It's derivative of v. dv over dt. 25 pi h becomes what? The coefficient stays, and then h turns into dh dt. Okay, let's look at some information here. Water is filling in at a rate of 3 cubic centimeters per minute. So what is that referring to? Cubic centimeters per minute. Which one is this referring to? EV, yeah, because you see cubic centimeters. If it's centimeters per minute, then that'll be a better one for height, but that cubic centimeters reminds us that this is a volume related value. So dv over dt equals 3. And how fast is the height of the water increasing? What are we looking for? dht. So we plug that in here. So 3 is equal to 25 pi dht. Divide both sides by 25 pi. Careful that you leave the pi in the denominator. All right, let's turn to page 12 and let's do another related rates involving trig. And then we can move on to page 13. Okay, you guys did this already for homework, but I want us just to kind of walk through this. It says in the figure shown, hot air balloon is rising straight up from the ground and is tracked by a television camera 300 feet from liftoff point. At the moment that the camera's elevation is pi over 6, the balloon is rising at a rate of 80 feet per minute. At what rate is the angle of elevation changing? So we're looking for d theta dt, which means that anything that's involving theta, we got to create a trig equation. So what trig equation can we use that will hit theta, 300, and the y? Sine, cosine, or tangent? Tangent, yeah. So tangent theta equals opposite over adjacent. If it helps, you can pull that 300 out as 1 over 300 times y. So get it ready for power rule. So let's go ahead and find the derivatives here. So tangent theta's derivative is what? Secant squared, right? Secant squared theta, d theta dt is equal to 1 over 300 times dy dt. Okay, at what rate is the angle of elevation changing? So we're looking for d theta dt. That's our ultimate goal for this problem. We know that the balloon is rising at a rate of 80 feet per minute. What do you think that's referring to? dy dt. So we have dy dt. We're looking for d theta dt, but we want to find a replacement for the entire secant square theta. But to do that, we need some information here. We need to at least have this value so that we can do Pythagorean theorem, right? We need at least two sides of a triangle to do Pythagorean theorem. So what can we do to solve for y? What information do we have that can help us solve for y? Okay, we do have this, right? At the moment, the camera's angle of elevation is pi over 6. So if we take that theta pi over 6, put it into tangent theta, we can solve for y. So we can say tangent of pi over 6 equals y over 300. Y cross multiply, use our calculator. I get y is equal to 173. And then Pythagorean theorem can help me find my hypotenuse, a squared plus b squared equals c squared. Ends up giving me 346. So I can find an entire replacement for secant of theta. Secant is what? What's the relationship for secant? Hypotenuse over adjacent. Okay. So if I take that fraction, I square it, I get a decimal value, multiply that or divide that over to the right side, and I can solve for d theta dt. Okay, so take that number, take this number divided by this number, solve for d theta dt, and I get 0.199. Which is around 0.2. Yes, question.
So is this what one multiple, is this how long one multiple choice problem would take on?
Some are a little bit longer than others, so I think they all vary. Some is just like 2-3 steps, others are a little bit longer. Right. I'm sorry? On the AP exam? On the AP exam, you're gonna have on the non-calculator, it's going to be 30 questions in 60 minutes. And then the calculator section is 15 questions, 45 minutes, which is like 3 minutes per problem.
So the calculator one's more complex.
Not really.
Not really.
I think the calculator question, well, calculator portion sometimes don't take as long. So it is a little bit strange why they give more time on the calculator section. So, but on my multiple choice test, you are going to expect. I do want you to show work because I'm grading you on the work. But you know, if it's on the AP exam, if you know the answer, you move on. You don't have to show all your work, so you can be a little faster, a little bit more efficient.
How many FRQ sections are do you have?
2 FRQ sections. So
Calculator, nothing.
calculator for numbers 1 and 2, and then 3 through 6. The next 4 problems is non-calculator. Yeah. Okay. Yeah. So you know, I would say a good strategy for multiple choice is, you know, you want to read the problem and at least, you know, try to see if you can understand what the first steps are. If you realize, wait, this is a long problem, you know, maybe I don't want to spend, you know, 5-6 minutes on this.
Go back.
Yeah, go back to it, right? So you almost want to kind of, you know, you want to read every problem, but if something's going to take a little bit longer, then circle it and then come back to it, right? The danger is that if you try to solve every problem at the in the order that they present you, you may run out of time, and then you never got to, you know, the last two problems, which were a lot easier. You know, you never know, right? The multiple choice questions are not in any order. It's random, so you're almost kind of hunting for the easier, faster problems, and then coming back to the ones that you know, you would rather run out of time with a problem that is longer than run out of time and not have any chance to work on, you know, a potentially easier problem. I don't think that would be an issue on the calculator section because you have more than enough time. But on the non-calculator, you know, you may feel a little bit rushed because, you know, 30 questions in 60 minutes, that's only 2 minutes average per problem. Now, having said that, some problems are going to be quick and easy. You can finish it in maybe 30 seconds. Other problems, though, may take, you know, more than 2 minutes. And then another thing to be aware of is on the when I give you guys a that final packet, which we're going to go through the week before your AP exams, there's going to be multiple choice practice tests in there from College Board. You can kind of see, you know, what the multiple choice questions can look like and what a full multiple choice test looks like. You're going to see that on the multiple choice calculator section. Not every problem requires a calculator, so it's just calculator active, meaning that if it is calculator appropriate, you have it in front of you for you to use, but don't feel like, wait, how am I supposed to use the calculator for this problem? I don't see how this applies. That's because a lot of times it doesn't. So even on the calculator section, maybe only half the problems will have anything to do with the calculator. Yeah, you have to decide. You have to decide reading the problem, is this even going to need a calculator? So I see some students, they try to force the calculator into a question. They feel like, wait, I have to use the calculator somehow, and they get stuck, not knowing that some of the problems are not even calculator related. Okay, page 13. Let me start with number 2. Well, let me, how about this? Yeah, let me start with number 2, and then and I'll come back to 1 if we have time. So number 2, it says the graph of our function has a point of inflection. So point of inflection, let's think about this. Point of inflection comes from what? Where do we find points of inflection? From which derivative?
Second derivative.
From second derivative. So is point of inflection simply where f double prime of x equal to 0? Or is there more to it? So if I find a critical point from the second derivative function, is that enough for me to call that a point of inflection?
No.
There has to be a what?
Change the sign.
Has to be a change in signs. So that is a that's a potentially a tricky thing. That the way that problem is asked, they provide you all the critical points, and if you don't go and test if there's a change in signs, then you may be tempted to pick a point that is a critical point, but not a point of inflection. Okay, so we got to take an additional step. This is not enough. We got to also create a sign line and check to see, you know, if there's no change from concave up to concave down or concave down to concave up, it's not a point of inflection. But we are going to set f double prime equal to 0. That is the first step. We need to find the candidates, but it also needs to have a change in sign on both sides of that critical point. Okay, so let's make our way down to the second derivative. Y prime is equal to, what's y prime first of all? Y double prime is equal to minus 12x. Okay, we set f double prime equal to 0. I can factor out a 12x. Okay, what's left? Just x, right? X minus 1. Okay, so I set both equal to 0. 12x equal to 0. X equals what? If I set 12x equal to 0, x equals just 0. If I set x minus 1 equals 0, and I get x equals 1. So if we stop here, we may be tempted to choose 0, 0, and 1, negative 1, because these are critical points, but we really should do what? To confirm that this is a point of inflection. Create a sign line. If there's no change in sign, then that critical point is not a point of inflection. So we can choose points on either side here. I'll choose negative 1 here. I'll choose 1/2. And I'll choose 2. Now, where do these points plug into if we want to test concavity? Is it to the original f prime or f double prime? Which prime? We want to test concavity, though. F double prime, yeah. F prime will tell you slope. F double prime will give you concavity. So either of these are fine. I like to do it in the factor form. I can gather my positive and negative signs a little bit faster. So negative 1 for x. 12 times negative 1 is negative. Negative 1 minus 1 is negative. 2 negatives makes a what? Positive. So this side is concave up. Plug 1/2 in. 12 times 1/2 is positive. 1/2 minus 1 is negative. Positive times negative is negative. Okay. Plug 2 in. 12 times 2 is positive. 12 minus 1 is positive. Positive. Okay. So in this case, looks like this is the answer, but I've seen enough cases where if you didn't go through this, if the signs don't change, then we can't call that a point of inflection. So just be aware of that. Okay. In this case, it's actually a little bit easier because a student could just stop here and actually get to the right answer. But most of the time, a problem is going to purposely have one that doesn't change signs, so that students can be tested to see, are they truly going through the full process of checking for point of inflection, or are they just stopping at the critical point and then just calling any critical point a point of inflection? Okay, actually, I want to do number 3 with you as well. Number 3 is called the second derivative test, and this one is one that we're less familiar with because we just don't see enough instances of this. But the whole purpose of second derivative test is using the second derivative function to confirm if there's a relative max, relative min. Okay. The test for concavity and second derivative test, they both involve the second derivative function, but they have different purposes. This is testing for concave up, concave down, point of inflection. This is testing for relative max, relative min. Right. So this does the same thing as a first derivative test. But it's kind of like a roundabout way of gathering information. So here's number 3. It says if f prime of 5 is equal to 0 and f double prime of 5 is equal to negative 3, decide at this point, is there a relative max, a relative min, or neither? Let's see if we can say this into words here. F prime of 5 is equal to 0. Can you describe what information is that providing us about this graph? Yeah, so at x equals 5, there is a what? The graph is experiencing a slope 0. What can a slope 0 look like? It could be a relative max, it could be a relative min, it could be neither. But we know it could be one of these options, right? But we don't know what that slope 0 is going to look like around that slope 0, but we know there's a slope 0 at 5. So we still don't know exactly which option this is. Now, this second may kind of give us more, shed more light on what's happening. F double prime of 5 is equal to negative 3. can you describe at that same point? These are both describing the same point, but it's giving us a different set of information. What is this telling us about the graph? As x equals 5, my graph is concave down because my second derivative value is negative, right? So x equals 5, my function is concave down. So if it's concave down and slope 0, then which of these options will the graph look like? It will look like the first option, the second, or the third? First one. So if it looks like this graph, then what can we say is happening at x equals 5? That there must be a what? There's a relative max, yeah. And this is the application of the second derivative test. It's basically taking information from two different derivatives and then creating a visual connection with this and understanding that, okay, this must be the shape of the graph because there's a slope 0 and it's part of a concave down graph, so it must be relative max. Now, having said that, it feels easy seeing this graph in front of you, but the trouble that students have is they see that negative and they assume that negative means what? Means a smaller value, and then they would assume that it's relative minimum. Okay, so just be aware of that. That, you know, if we don't connect this with concavity, then, and we don't connect this with the shape, then it's easy for students to see that negative and think, okay, relative min, positive is relative max, but it's not, that's actually not the case, right? These are not actually physical points. These are actually concavity, describing concavity behavior of my graph. Okay, so your homework is to finish page 13 and 14. I will highlight some problems tomorrow in class, and then tomorrow in class, we'll finish 15 and 16 together. All right, can we get your phones? Yeah. Thank you. All right, sure. You want those?
Oh, you were good. I barely remember. I like one more. Okay, just sure. Yeah. We'll only give this 2 days to do it. Yeah. You're not doing that much time at all. Well, at least you're. I'm working my lawyer person by call. No, already.
No.
It's me and I get this like, and we are trying to get this up there. And that's one.
Like in
the
lunchroom.
All right, but we still have 2 assessments in April, so I couldn't get.
That's a message.
You wanna maybe send me some dates that we can target, so that, you know, yes, we have some stuff, that way, you know, before we know it's gonna be like end of April.
Yeah.
Like.
There's a change.
Hey, how are you?
Good. Do you want to first break?
No, I'll be in town. I'm gonna go watch, I'm gonna be out to Pensacola for a weekend,
Oh, nice.
the weekend right before we get back.
Or something's going there.
Oh, really?
Yeah.
Yeah.
Popular spot. I'm staying here. I'm staycation.
Okay, good.
We might keep going. Like, I think we're going to trip to like Alabama for a couple of days.
We're in Alabama.
Like it's like Irondale. It's nearly Birmingham.
Oh, yeah. It's not too far, like 2 hours, 2.5 hours away.
Only for 2 days. First time I'm staying here. See you back.